All right, let's talk about building something. Anyone can sketch a house on a napkin, right? But you need an architect for a solid blueprint that won't fall down. In the world of data, that blueprint is your database schema. And making it strong is a process called normalization. And trust me, it's absolutely critical. To see why, we're going to investigate one single table that looks simple, but is secretly a disaster waiting to happen.
So here's our mystery. At first glance, this table seems fine. It's got all the project data in one place, seems easy enough. So what's the big deal? Well, this simple little table is actually a ticking time bomb, filled with errors that are just waiting to blow up your data's integrity. And here it is, our scene of the crime. The project data table. It tracks which employees are on which projects. Simple enough. We've got project info, employee info, department info. But wait, look closer. See Jay Smith? He's on 2 projects, so his name, his department, and even his phone number are listed twice. This repetition, this right here, is the root of all our problems.
Okay, so let's put on our data detective hats and really dig into the flaws hiding in this design. We're going to throw a few real-world situations at this table and watch exactly where and how it breaks. Here's test number 1. This is something that happens literally every day in any company. An employee, Jay Smith, gets a new phone number. Our job, just update the database. Should be easy, right? Well, nope, not so easy. Because Jay Smith's phone number is in 2 separate rows, someone has to remember to find and change it in every single place. If you miss just one, and people always do, your database is now inconsistent. You have 2 different phone numbers for the same person. This is called an update anomaly, and it's a huge deal. Your database is now actively lying to you. So we've seen what the problem is, this update anomaly. But to really fix it for good, we need to understand why it's happening. We've got to uncover the hidden logic, the invisible rules that connect all these columns together. So I'll ask you, just look at this table. What piece of information determines another? Like, if I tell you an employee ID, what else do you automatically know for sure? Thinking about these connections, that's the key to cracking this whole case. And if we actually map out that hidden logic, the dependencies become crystal clear. See that? Proj ID points directly to Proj name. You give me the ID, I'll give you the name. Every time. Same goes for Emp ID. It determines the employee's name, their department, and their phone number. These connections have a name. They're called functional dependencies. Let's give it a proper definition. A functional dependency, which we write as A with an arrow pointing to B, just means that if you know the value of A, there is only one possible value for B. A great example is your social security number. It determines your name. But your name doesn't determine your social security number because lots of people could have the same name. Getting a handle on these dependencies is really the bedrock of good database design. Okay, deep breath. We found the problem, we figured out the cause, now it's time for the solution. We're going to use a process called normalization to clean up this disaster. Think of it as a step-by-step guide for tidying up data to get rid of those dangerous anomalies once and for all. And here's our playbook. We're going to focus on the first 3 stages of cleanup, called normal forms. Each step is designed to fix a very specific kind of structural problem, pushing our data closer and closer to being perfectly organized and totally reliable. Let's get to it. So, let's start the big cleanup. Now, our original table is already in what's called first normal form, basically because every box has just one value in it. So our first real job is to get this thing into second normal form. So what the heck is second normal form, or 2NF? The rule is actually pretty simple. Every column that isn't part of the main identifier, the primary key, has to depend on the whole key, not just a little piece of it. This rule specifically goes after tables like ours, which have a key made up of more than one column. And here is exactly where our design breaks that rule. See, the primary key here is the combination of Proj ID and Emp ID. But notice how Proj name only really cares about the Proj ID part. And all the employee details? They only depend on the Emp ID part. These are called partial dependencies, and they are a big no-no in 2NF. So what's the fix? We break the table apart. It's like sorting your laundry. We create a projects table for just project stuff. We create an employees table for just employee stuff. And then we create this new little table in the middle, project_assignments, that has one single job, connect projects to employees. Now, every single idea has its own separate tidy home. And just to show you this isn't some abstract theory, this is what it actually looks like in code. This is the SQL command you'd use. You're just telling the database, hey, make me a table called projects, give it these 2 columns, and make proj ID the unique identifier. See? It's clean, it's focused. We're so much better off now, but there's one last cleanup step we need to take, getting to third normal form, or 3NF. This rule is all about hunting down something called transitive dependencies. That's just a fancy way of saying a situation where one regular column is determining what another regular column should be. It's like an indirect dependency chain. Let's go back and look at our new employees table. Let's say in this company, every department has its own phone line. Well, if that's the case, then the department name actually determines the department phone number. This creates that transitive dependency we were just talking about. The emp ID tells you the department, and then the department tells you the phone number. We can clean this up even more. And you probably know the drill by now, right? We applied the exact same logic. We split the table. We create a brand new departments table to hold only department info, like the phone number. Now the employees table just needs to know which department someone works in, not all the details about that department. And here's the code for that final piece of the puzzle. A super simple, elegant table just for storing department names and their phone numbers. Now, every single piece of data has one and only one place where it lives. No more repetition. So, after all our detective work, after all that cleaning up, what's the final result? Let's take a look at the beautiful, stable blueprint we've just created, a design that's built from the ground up for data integrity. And there it is, our final normalized schema. 4 clean, distinct tables, each one focusing on a single thing. Projects, employees, departments, and the links between them. It's honestly a thing of beauty. Every piece of info has a single authoritative home. And this is the real takeaway. Let's look at the before and after. We started with this chaotic table, full of update anomalies and tons of redundancy. And now we have a design that guarantees data integrity. If a department's phone number changes, you change it in exactly one spot. That's it. We've built a rock-solid foundation. But this brings us to one last really interesting question. We've created this perfectly organized database, which is amazing for storing data without errors. But by splitting our data into 4 separate tables, have we actually made it slower to pull all that information back together for a big report? Well, that's a fantastic question, and a story for another explainer. Thanks for tuning in.